Hey, this is Warren Redlick with a deep dive into what it's going to take to make FSD beta become full self-driving and lead to level 4, level 5, and robo-taxis. I broke it up into chapters, so look below for those. And of course, check out the Cybertruck t-shirt and other t-shirts at elonbits.com. Links in the description below.
By vector space, I mean, like, you've got cars and humans and lane lines and curves and traffic lights and that kind of thing. Once you have an accurate vector space, the control problem is similar to that of a video game, like a Grand Theft Auto or Cyberpunk. If you have accurate vector space, the control problem is, I wouldn't say it's trivial. It's not trivial, but it's not like some insurmountable thing. But having an accurate vector space is very difficult.
So this is the big challenge of making full self-driving work, is an accurate vector space. The way I'll phrase that to be a little different than Elon is an accurate 3D model of the world, not just of the way the world is, but understanding what objects are and what they're likely to do and where they're likely to move. If you have a full understanding of the 3D vector space that you're dealing with, it's easier to navigate that world. So I want to show the challenge of an accurate vector space from my own experience. This is from my car crossing over an intersection, and what you're going to see is that there's this blue line here projecting out from the car, and the blue line represents where the car thinks it's going. And what it's doing is there's 3 lanes over here. There's a left-hand straight lane, there's a right-hand straight lane, and there's a right turn lane. What the car needs to do, and right now you can see the car is in the right-hand straight lane. What the car should do is it should be wanting to get into the left-hand lane to make a left-hand turn coming up. And the problem is that the car has chosen the right lane. In this particular video, I let it choose the right lane, which creates problems. But the key point was to watch how the blue tether flickers as to what lane it wants to be in. This is a representation of the fact that the car isn't sure what's on the other side of the intersection. I know it from driving it. I can see it as I'm driving it. There's a left-hand straight lane, there's a right-hand straight lane, there's a right turn lane. When I'm driving the car and an FSD beta and I come from this direction and it makes a right turn, it almost always goes into the right-hand right turn lane instead of going into the right-hand straight lane. And it's just that the car doesn't have I think what's going on is the car doesn't have a fully accurate understanding of the 3D space that it's operating in. And that is the big challenge to get navigation to work. Once it understands, okay, I don't want to be in the right turn lane because the right turn lane doesn't take me where I want to go. When I first make my turn, I should go into the right-hand straight lane, or from normal traffic rules, what most of us do is we go straight into the left-hand lane because we know that's where we need to go. And if I've got a clear right turn and I'm the only right turn lane, I can go ahead and do that. So when I'm approaching this intersection, navigation tells the car to be in the left lane, but as it approaches the intersection, because of this confusion, the car tries to get in the right-hand straight lane. And this is all based on a fundamental problem that the car doesn't have a full grasp yet of the 3D space it's operating in. The vectors, the understanding, I think it's actually confused about the line between the left-hand straight lane and the right-hand straight lane when I look at it. But let me just show you what it looks like here. Just watch the blue line here. You can see that it's flickering. It's trying to decide where it's going to go, and it's not sure what lane it needs to go in. See how it's flickering left and right? It's not sure where to go. So the fundamental challenge that FSD faces right now is developing an accurate 3D picture of the world, a 3D model of the space that it's operating in. It needs to know which lane it's in, which lane it's going in. That's a lane line. This is a stop sign. This is a traffic light. That's a person. And then it also makes predictions about where people are going to move, where cars are going to move. And if it has really good identification of objects, understanding of what those objects are, and is able to make good predictions of where they might move if they're going to move, it's so much easier to navigate that space. And as long as it has that uncertainty about where it's going, what space it's heading towards, it's hard for it to navigate that. If it thinks it's supposed to be in the right lane when it's supposed to be in the left lane, then it's going to navigate to the wrong lane. And that's the underlying challenge. So let's listen to some general stuff that Elon has to say in his conversation with Lex Fridman. This is from back in December. Let's listen a little bit more about what Elon has to say about the general problem, both Elon and Lex.
The compute, the sensors, the things I maybe care and love about most is the stuff that Andrej Karpathy is leading with the data set selection, the whole data engine process, the neural network architectures, the way that's in the real world that network is tested, validated, all the different test sets, versus the ImageNet model of computer vision, like what's in academia is like real world artificial intelligence.
I just wanted you to hear that. So this is Lex Fridman, who's a researcher in artificial intelligence at MIT and also a prominent podcaster, obviously, our YouTuber podcaster. And Lex is describing the complexity of one part of FSD. There is so much going on in full self-driving, and Elon's going to talk about that a little bit next. Lex is fascinated with what Andrej Karpathy is doing. There's so much more going on. We're going to dive into that a bit here and there. But listen to what Elon says next.
And Andrej's awesome and obviously plays an important role, but we have a lot of really talented people driving things. And Ashok is actually the head of autopilot engineering. Andrej's director of AI
stuff. Yeah. So I'm aware that there's an incredible team of just a lot going on.
Yeah, just obviously people will give me too much credit and they'll give Andrej too much credit. So,
and people should realize how much is going on under the hood.
It's just a lot of really talented people. The Tesla Autopilot AI team is extremely talented.
It's a tremendously complex problem. There's a lot of people working on Tesla's autopilot team, Tesla's AI team, handling a lot of different issues. And we're going to hear a lot more about the complexity of this in the course of this video. It's really important to understand a huge number of extremely talented people are working really hard on this extremely difficult problem. And you're going to see through this video that they are making progress and they are getting where they need to be, that we're going to have full self-driving soon. It's this fundamental problem. Really, the underlying biggest problem is developing a vector space. Can they take incoming photons and convert it to a vector space so the car knows what it needs to navigate?
What are some insights you've gained over those 5-6 years of autopilot about the problem of autonomous driving? So you leaped in having some sort of first principles kinds of intuitions, but nobody knows how difficult the problem.
I thought the self-driving problem would be hard, but it was harder than I thought. It's not like I thought it would be easy. I thought it would be very hard, but it was actually way harder than even that.
So this is one of those things that Elon gets criticized for saying we're going to deliver self-driving next year, back in 2015 or whatever. And Elon is constantly optimistic that we're going to be able to solve this problem. And the reality of self-driving is it just ends up being a much harder problem than we thought. I don't blame Elon for getting that wrong. He was optimistic they would be able to solve the problems, and they just keep finding more problems. And life is what it is. He now has a much better understanding of how difficult the problem is. And this is why I believe Elon when he says we're going to deliver better than human this year. And you'll hear that in this call, why he thinks that this year, 2022. The video is actually from 2021. He has a better understanding of this problem than anyone outside of Tesla now, because of the amount of time that he's put into it, the amount of time the team has put into it. I think they really finally have a grip on what needs to be done to get there. So let's listen a little bit more about the complexity of this problem.
I mean, what it comes down to at the end of the day is to solve self-driving, you basically need to recreate what humans do to drive, which is humans drive with optical sensors, eyes, and biological neural nets. That's how the entire road system is designed to work, with basically passive optical and neural nets biologically. And now that we need to, for full self-driving to work, we have to recreate that in digital form. That means cameras with advanced neural nets in silicon form, and then it will obviously solve for full self-driving. That's the only way. I don't think there's any other way.
One key point here is there's people who think we need LiDAR, we need radar, we need other sensors, we need HD maps, and humans drive the road system we have using 2 cameras and the neural nets that are in our heads. That's how we drive. Tesla FSD drives with 8 cameras and advanced high performance digital computers and advanced software. And the sense that I have is that when you have 8 cameras instead of 2, when you have high performance computing, once the software is right, you will be able to outperform human drivers. The system will never get drunk. The system won't get distracted by the girl in the bikini. Yes, I like bikinis. No, I'm not apologizing for it. The system will not get medicated. The system won't get sleepy. There's so many advantages to full self-driving, and it has 8 cameras, so it's got a constant 360-degree view. It's got a high frame rate. It should be able to build a better 3D picture of the world than we can. We have great software in our heads, great hardware in our heads that has evolved to be able to do all this stuff as well as we do it. But the harsh reality is that computers will ultimately be better. It's just a question of when. And I think the answer to that question is next year. At end of this year, early next year.
But the question is, what aspects of human nature do you have to encode into the machine, right? So you have to solve the perception problem, like detect, and then you first, realize what is the perception problem for driving, like all the kinds of things you have to be able to see. Like what do we even look at when we drive? There's I just recently heard Andre talked about at MIT about like car doors. I think it was the world's greatest talk of all time about car doors.
Yeah.
The fine details of car doors. Like what is even an open car door, man? So like the ontology of that's a perception problem. We humans solve that perception problem, and Tesla has to solve that problem.
Lex is pointing out just another example of the complexity of the problem here is you're driving down the road and there's a car door and it's partially open or it's fully open or it's open on the right side or it's open on the left side and there's a person standing near it. And we process that with our software to figure out, okay, what we see it, the photons hit our eyes, we recognize the situation, we make a judgment about what to do. The car has to do the same thing. The car, in a sense, has to know that's an open car door. That means somebody might be coming in or out of that car. And the car has to make judgments based on that. And that's just a matter of having a lot of data. That's how neural nets work, is you give them a lot of data and they figure it out. You're going to go a little bit more into this game theory question next.
There's the control and the planning coupled with the perception. You have to figure out like what's involved in driving, like especially in all the different edge cases. And then, maybe you can comment on this. How much game theoretic kind of stuff needs to be involved, at a 4-way stop sign? As humans, when we drive, our actions affect the world. Like,
sure,
it changes how others behave. Most autonomous driving, you're usually just responding to the scene, as opposed to like really asserting yourself in the scene. Do you think?
I think these sort of control logic conundrums are not the hard part.
The control problem is not the hard part. What you're going to hear next is the hard part is building the vector space, building the 3D model of the world, which is related to that car door issue that Lex was talking about earlier. Building a 3D space, building a 3D model of the space and representing everything and predicting where it's going to move. Once you have all that done well, it becomes easy to navigate through that space. But if you don't have a good, accurate representation of the 3D space that you're operating in, and you don't have good predictions, it becomes much harder.
What do you think is the hard part in this whole beautiful, complex problem?
So it's a lot of friggin' software, man. A lot of smart lines of code.
What is the hard part? So it's a lot of software, it's a lot of lines of code, but let's get into it. I played this clip at the beginning, but this is the hard part.
So it's a lot of friggin' software, man. A lot of smart lines of code. For sure, in order to create an accurate vector space, like you're coming from image space, which is like this flow of photons, going to the camera. So you have this massive bit stream in image space, and then you have to effectively compress a massive bit stream corresponding to photons that knocked off an electron in a camera sensor, and turn that bit stream into vector space. By vector space, I mean like you've got cars and humans and lane lines and curves and traffic lights and that kind of thing. Once you have an accurate vector space, the control problem is similar to that of a video game, like a Grand Theft Auto or Cyberpunk. If you have accurate vector space, it's the control problem is I wouldn't say it's trivial. It's not trivial, but it's not like some insurmountable thing. But having an accurate vector space is very difficult.
Having an accurate vector space, that is the big challenge. I just want to show you here, this is in a sense one way of looking at the challenge of what Tesla's trying to do. Is you're driving down the road and you've got to identify all these different things that are going on. You've got to identify lane lines. You've got lane lines here. You've got to identify objects, vehicles. You've got to identify traffic lights. You've got to identify, what the vehicle, what the object is. So it's a car. How far away is it? How fast is it moving? Where is it likely to go? Is this vehicle likely to swerve in front of you? Is this vehicle likely to stop? Is it going to keep going? There's all these, and then there's an intersection here. So there's going to be cars coming this way, and figuring out where different objects are, how far away they are from your vehicle, where they're likely to move, what the lanes mean. Is this a straight lane? Is this a left turn lane? All these different things that you have to figure out. That is a part of the problem. And by vector, each object can be thought of as a vector, and each vector has properties. So the properties might be it's a car, might be it's a truck with a trailer, might be the physical location of the vehicle in the vector space, the velocity of the vehicle in the vector space, and then predictions about what it's likely to do. These are all components of a vector in some sense. Next, Lex and Elon get into what the brain does to process the video data coming in through our eyes, and that relates to what the car's FSD computer is going to have to do to manage the video data coming in through its cameras. Listen to this.
Humans don't give enough respect to how incredible the human perception system is, to mapping the raw photons to the vector space representation in our heads.
Your brain is doing an incredible amount of processing and giving you an image that is a very cleaned up image. Like when we look around here, we see, like you see color in the corners of your eyes, but actually your eyes have very few cones, like cone receptors in the peripheral vision. Your eyes are painting color in the peripheral vision. You don't realize it, but their eyes are actually painting color. And your eyes also have like this blood vessels and all sorts of gnarly things. And there's a blind spot, but do you see your blind spot? No, your brain is painting in the blind spot. And you're going to do these see these things online where you look here and look at this point and then look at this point, and if it's in your blind spot, your brain will just fill in the missing bits.
So cool. The peripheral vision is so cool. It
Yeah.
makes you realize all the illusions for vision science. It makes you realize just how incredible the brain is.
The brain is doing a crazy amount of post-processing on the vision signals from your eyes.
One of the interesting details here is the brain has to work around the failings of the human eyes. Number one, we're only looking in one direction. Number two, there's blood vessels, there's blind spots, and the brain has tremendous hardware and software in terms of the hardware of the brain and the software that the brain effectively has to work around the flaws in our vision to enable us to paint a 3D picture of the world or a vector space. Not sure exactly how we think about that space, but we inherently envision some sort of way of we identify objects and we predict what they're going to do and we navigate the space, right? That's what we do when we're driving. And it's amazing what the brain is able to do. They're going to talk more about the brain next.
Even once you get all those vision signals, your brain is constantly trying to forget as much as possible. So human memory is perhaps the weakest thing about the brain is memory. So because memory is so expensive to a brain and so limited, your brain is trying to forget as much as possible and distill the things that you see into the smallest amounts of information possible. So your brain is trying to not just get to a vector space, but get to a vector space that is the smallest possible vector space of only relevant objects. You can sort of look inside your brain, or at least I can, like when you drive down the road and try to think about what your brain is actually doing. Yeah. Consciously, you'll see a car because you don't have cameras. You don't have eyes in the back of your head or the side. So you say like, you basically your head is like you basically have like two cameras on a slow gimbal.
Two cameras on a slow gimbal, meaning we have two cameras here, and the gimbaling is turning your head to one side or the other. We don't turn our heads that fast compared to what a robot might be able to do. We can't see to the side instantly like FSD can because FSD has 8 cameras around. So we're limited to these 2 cameras on a slow gimbal, and yet the brain is able to do a lot with that.
And eyesight's not that great. And people are constantly distracted and thinking about things and texting and doing all sorts of things they shouldn't do in a car, changing the radio station, having arguments. Like, when's the last time you looked right and left, and and rearward, or even diagonally, forward, to actually refresh your vector space? So you're glancing around, and what your mind is doing is trying to distill the relevant vectors, basically objects with a position and motion, and then editing that down to the least amount that's necessary for you to drive.
So it's an important detail here is, number one, your brain has to put all that together and basically create a vector space of objects that you see or that you know are there because you've seen them before, and predicting whether they're likely to come into your path or how you need to avoid them or how you need to navigate around them. And at the same time, there's this challenge of memory, which is a huge challenge for digital computers. It's a challenge for our brains as well, that we have to manage that and compress the information to a small amount of data that our brain is able to process at high speed so that we can navigate our vehicle through this complex 3D space that we're driving in. Same challenge for FSD. I just have to interrupt here. So I've been editing this video and I thought about this part and I drove my car, and I don't feel like when I drive my car, I'm constructing a vector space. I'm mainly playing what Andrej Karpathy calls the line following game. I'm making sure my car is staying in my lane. That's really more of a subconscious thing than a conscious thing. I'm driving the car, I'm keeping my eyes open, and I don't really track where all the vehicles are, where all the objects are. I'm basically just keeping my eyes open, and I'm watching for threats. The defensive driving is you're driving down the road and you're looking for things that might be problems. You're looking for that car that might cut in front of you. You're looking for that kid on the side of the road who might jump out in front of you. So you notice certain objects, and they draw a lot of your attention. And the vast majority of objects that you might see, you probably don't even notice at all. I'm not constructing a vector space and thinking about everything around me. I don't think I'm doing that. I can't say for sure. Maybe Elon his mind works differently when he's driving than mine does. I would just ask you to think about, how does your mind work? I don't think it's necessarily the case that we're all driving down the road constructing vector spaces and our memory is working in a certain way. There are probably moments where we see kids walking past the school bus or behind a truck, and we're aware that they're there because they're objects that we're paying attention to. But what FSD is doing is it's paying attention to every object because it can. It is capable of seeing everything. Our compute is probably more efficient because we are much better able to ignore anything that doesn't really matter. That's just my take on it. I don't think that the computer in the car is capable of knowing what to ignore, and it doesn't need to. It's able to pay attention to everything, and there's some very, very small probability risks from things we probably wouldn't notice that the car will notice, and it's one of the things that will make the car safer. Sorry for the interruption. Best part is no part is another t-shirt on elonbits.com. Check out elonbits.com. Now back to our story.
It does seem to be able to edit it down or compress it even further into things like concepts. So it's like it goes beyond, the human mind seems to go sometimes beyond vector space to sort of space of concepts, to where you'll see a thing. It's no longer represented spatially somehow. It's almost like a concept that you should be aware of. Like if this is a school zone, you'll remember that as a concept, which is a weird thing to represent. But perhaps for driving, you don't need to fully represent those things, or maybe you get those kind of indirectly.
You need to like establish vector space and then actually have predictions for those vector spaces. Just imagine there's like a large truck or something blocking sight, but before you came up to the truck, you saw that there were some kids about to cross the road in front of the truck. Now you can no longer see the kids, but you need to be able. But you would now know, okay, those kids are probably going to pass by the truck and cross the road, even though you cannot see them. You need to remember that there were kids there, and you need to have some forward prediction of what their position will be.
It's a really hard
at
problem.
The time of relevance.
So with occlusions and computer vision, when you can't see an object anymore, even when it just walks behind a tree and reappears, that's a really, really, I mean, at least in academic literature, it's tracking through occlusions. It's very difficult.
Yeah, we're doing it.
I understand this.
Yeah.
This is a very hard problem. They talked about this at AI Day, that they're able to see where people are moving, where objects are moving, and they're able to predict where they're going to continue to move after they're occluded. And they're going to talk more about this concept of object permanence as they go deeper into this.
Object permanence, like the same thing happens with the humans with neural nets. Like when like a toddler grows up, like there's a point in time where they have a sense of object permanence. So before a certain age, if you have a ball or a toy or whatever, and you put it behind your back and you pop it out, if they don't, before they have object permanence, it's like a new thing every time. It's like, whoa, this toy went poof, disappeared, and now it's back again, and they can't believe it. And that they can play peekaboo all day long because the peekaboo is fresh every time. But then we figure out object permanence. Then they realize, oh no, the object is not gone; it's just behind your back.
Sometimes I wish we never did figure out object permanence. So that's an important problem to solve.
Yes. So like an important evolution of the neural nets in the car is memory across both time and space. Now you can't remember, like you have to say, like, how long do you want to remember things for? And there's a cost to remembering things for a long time. So you like run out of memory if you try to remember too much for too long. And then you also have things that are stale if you remember them for too long. And then you also need things that are remembered over time. So even if you, like, say, have, like, for argument's sake, 5 seconds of memory on a time basis, but like, let's say you're parked at a light and you saw, use a pedestrian example, that people were waiting to cross the road, and you can't quite see them because of an occlusion, but they might wait for a minute before the light changes for them to cross the road. You still need to remember that that's where they were. And that they're probably going to cross the road, type of thing. So even if that exceeds your time-based memory, it should not exceed your space memory.
So there's this interesting challenge of remembering both time, how much happened in the last 5, 10 seconds, or however long you have to remember back in time, and distance, how much happened in the last 50 yards, 100 yards, 150 yards. How much does the car need to remember? And for specific objects, does it need to remember longer? Does it need to remember farther away? These are all challenges our brain manages, and these are the same challenges that the car needs to manage. And both our brains and the car's digital system have a limited amount of memory, so you can't memorize everything. You can't memorize everything forever, so you have to make choices, and this is one of the challenges they have in designing the software for FSD. And they're making great progress on it. They're doing really well. Again, this is something they talked about at AI Day, remembering over a period of time and remembering over distance. These are challenges that they're managing, and they're doing well at it. Next is a couple of really interesting bits about computational complexity, the amount of compute you have available, and then the next thing after that, it relates to latency and jitter. This is really interesting stuff. It's deep, it's complex, it's technical, it's nerdy, but this is important stuff for understanding where FSD is going.
If you see the full like array of neural nets that are operating in the car, it kind of boggles the mind. There's so many layers. It's crazy. And we started off with simple neural nets that were basically image recognition on a single frame from a single camera, and then trying to knit those together with C. I should say we're really primarily running C here because C++ is too much overhead, and we have our own C compiler. So to get maximum performance, we actually wrote our own C compiler and are continuing to optimize our C compiler for maximum efficiency. In fact, we've just recently done a new rev on a C compiler that'll compile directly to our autopilot hardware.
So you want to compile the whole thing down and with your own compiler.
Yeah.
Like, so efficiency absolutely. Here, because there's all kinds of compute. There's CPU, GPU, there's like basic types of things. And you have to somehow figure out the scheduling across all of those things. And so you're compiling the code down that does all, okay. So that's why there's a lot of people involved.
This is just another step in understanding the complexity of what's going on in Tesla's FSD project. There's parts of the code that are in what's called C, which is computer programming language. Elon's referenced C++, which is a more recent computer programming language, but it has extra baggage, so that means it uses more compute, and they're trying to make their chips run as efficiently as possible. So they use C, and compiling means you write some code, and instead of the computer running the code, you compile the code down, and compiling makes the code run faster. And having your own compiler allows you to compile the code in a way that it runs even faster. And the faster your code runs, the more efficient it is in terms of memory and the use of the CPU time and the GPU time and everything else, the more capable your computer is going to be of handling the problems that you need to handle.
There's a lot of hardcore software engineering at a very sort of bare metal level, because we're trying to do a lot of compute that's constrained to, our full self-driving computer. So, and we want to try to have the highest frames per second.
Frames per second, if you're looking at movies, they might be in 24 frames per second. TV might be 30 frames per second, roughly, or 29.97 frames per second, something like that. That's the number of images per second that you're processing. And the goal is to have a higher frames per second. That means you're able to see the world in shorter bits, so that when you're making decisions, the data you're based on is more recent. In other words, if you're only processing 1 frame per second, you might be making a decision on something that happened 0.99 seconds ago. But if you're processing 60 frames a second, then the last bit of data you have is only 1/60th of a second ago, which means you're making decisions on more current data. That's really important. And there's a lot more to why frame rates are important, because you get more information, you're able to work off of more.
In a sort of very, very finite amount of compute and power.
And what's going on underneath is you've got a finite amount of compute and power and memory, and you're trying to optimize so that you can do as much as possible with the computing hardware you have. Yes, hardware 4 is coming. That will probably enable more, but the team believes that the hardware they have in hardware 3, which is in current Model 3s, Ys, S's, and X's, that is enough to enable it. It's just a software problem of being able to process the incoming photons and turn it into a vector space. And they're making great progress at that.
And so there's actually a lot of work done by some very talented software engineers at Tesla that at a very foundational level to improve the efficiency of compute and how we use the trip accelerators, which are basically doing matrix math dot products, like a bazillion dot products. And it's like, what are neural nets? It's like, compute-wise, like 99% dot products.
One of the things I hear Elon say a lot is that a lot of compute is dot products. There's this matrix math that's going on, which makes sense. You're working with a vector space and matrix math. This goes together. It's basically linear algebra. This is one of the keys, is that if you can do matrix math really efficiently and you're working with vector space, then you can do a lot better job of using your computer more efficiently.
We really put a lot of effort into the efficiency of our compute.
And you want to achieve as many high frame rates, like a video game. You want full resolution, high frame rate,
low latency, low jitter. One of the things we're moving towards now is no post-processing of the image through the image signal processor. What happens for cameras is that, almost all cameras, is there's a lot of post-processing done in order to make pictures look pretty. Mm-hmm. And so we don't care about pictures looking pretty. We just want the data. So we're moving to just raw photon counts. So the system will, like, the image that the computer sees is actually much more than what you'd see if you represented it on a camera. Wow. It's got much more data. And even in very low light conditions, you can see that there's a small photon count difference between this spot here and that spot there, which means that it can see in the dark incredibly well, because it can detect these tiny differences in photon counts.
Here, Elon's going to talk about latency and jitter. Latency is the gap between when the data comes in and when the car decides what to do. There's this window of time, and the shorter you can make that, the more relevant the data is to the decision the cars are making. And then there's also this challenge of jitter, which is the latency itself can be variable. And if you can get latency and jitter down, the car makes better decisions quicker. Listen to Elon explain this in some depth.
And then we also save 13 milliseconds on latency.
From removing the post-processing on the image?
Yes. Yeah. Because we've got 8 cameras, and then there's roughly, I don't know, 1.5 milliseconds or so, maybe 1.6 milliseconds of latency for each camera, and going to just basically bypassing the image processor gets us back 13 milliseconds of latency, which is important. And we track latency all the way from, photon hits the camera to, all the steps that it's got to go through to get, go through the various neural nets and the C code, and there's a little bit of C++ there as well. Maybe a lot, but the core stuff is the heavy duty compute is all in C. And so we track that latency all the way to an output command to the drive unit to accelerate, the brakes to slow down, the steering, turn left or right. So, because you got to output a command, that's going to go to a controller, and like some of these controllers have an update frequency that's maybe 10 hertz or something like that, which is slow. That's like now you lose 100 milliseconds.
10 hertz is 10 times a second. 100 milliseconds, there's 10 groups of 100 milliseconds in a second. Elon's going to explain a little bit more next.
So then we want to update the drivers on the, like say, steering and braking control to have more like 100 hertz instead of 10 hertz. And you get a 10 milliseconds latency instead of 100 milliseconds worst case latency. And actually jitter is more of a challenge than latency, because latency is like you can anticipate and predict, but if you've got a stack up of things going from the camera to the computer through then a series of other computers and finally to an actuator on the car, if you have a stack up of tolerances, of timing tolerances, then you can have quite a variable latency, which is called jitter.
So there's two big topics that he's talking about here. One is latency, which is the delay between the time the light comes in the camera to the time that the vehicle makes a decision. And ideally, you'd have a fixed latency. You'd know how long it is from the time you got the information to the time you make the decision. But this jitter problem actually means you don't even know how much the gap is, because it might be 100 milliseconds, 1/10 of a second, or it might be 250 milliseconds or 1/4 of a second. And that extra time and that uncertainty about when things are going to happen makes it much harder to navigate that 3D model of the world when the model of the world is changing over time. And if you know exactly 100 milliseconds, then you can adjust for that. But if you're not sure whether it's 100 milliseconds or 250 milliseconds, it makes your 3D model of the world a little less perfect, your vector space a little less accurate, and it's harder to make good decisions about how to drive.
And that makes it hard to anticipate exactly how you should turn the car or accelerate, because if you got maybe 150, 200 milliseconds of jitter, then you could be off by up to 0.2 seconds, and this could make a big difference.
So you have to interpolate somehow to deal with the effects of jitter, so that you can make like robust control decisions. You have to. So the jitter is in the sensor information. Or the jitter can occur at any stage in the pipeline. You can,
if you have fixed latency, you can anticipate, and like say, okay, we know that our information is, for argument's sake, 150 milliseconds stale. Okay. Like so, for 150 for argument's sake, 150 milliseconds from Photons taking camera to where you can measure a change in the acceleration of the vehicle. Then you can say, okay, well, we're going to, we know it's 150 milliseconds, so we're going to take that into account and compensate for that latency. However, if you've got then 150 milliseconds of latency plus 100 milliseconds of jitter, which could be anywhere from 0 to 100 milliseconds on top. So then your latency could be from 150 to 250 milliseconds. Now you've got 100 milliseconds that you don't know what to do with. And that's basically random. Getting rid of jitter is extremely important.
So if you can bring latency down and you can bring jitter down, then the car will fundamentally make better decisions. I believe humans have about a 1/3 of a second latency, or 333 milliseconds. I think it depends on the human. Some humans react quicker, but something like 1/3 of a second. So if the car is down to 100 milliseconds or 150 milliseconds, it's got quicker reaction time than humans. But obviously the goal is to give it quicker and quicker reaction time, so you want to reduce latency, and more certainty on your reaction time, so you want to reduce jitter. I'm going to take a break in Elon and Lex talking, and I'm just going to try to relate what this all means. And I'm going to use the movie The Matrix to explain it. When he talks about the car using raw photon counts, check out how Cypher talks about how he sees the Matrix, the 3D space that the Matrix represents.
Yeah.
Do you always look at it encoded?
Well, you have to. The image translators work for the construct program. But there's way too much information to decode the Matrix.
I'm not sure how clear that was, but the point is that there's more information in the code than we can see with our eyes in the Matrix. And the same thing is true with the cars, that there's more information in the photons that hit the cameras than we're able to process when we look at a video image. And I just wanted to show you something else related to that. So down below me here, these are the 3 cameras at the front of the car. The center, there's 3 cameras looking forward from the center right above the rear view mirror inside the car. That there's all this photons coming in. There's 5 other cameras looking forward, sideways, back, and there's all these photons coming in. And then you look at how the computer can process that data. So over here you have the lens, and the photons come through the lens and they hit the sensor. This is the camera chip. And it goes in here from the sensor and you get raw data, which is basically raw photon counts. It may be a little more complicated than that, but it's generating photon counts. And now you go through this processor to convert that information to an image over here. And the thing is, the computer doesn't need to see the image. The computer can rely on the data just like Cypher relies on the data. Rather than having to see the space of the Matrix, Cypher can read the code and he can see the Matrix. And what happens to Neo at the end of the movie?
He is the one.
At the end of the movie, The Matrix, Neo is seeing the world in code instead of seeing the video image that we all see. I'm not sure it's a fair representation, but the idea is the car is seeing photon counts instead of seeing processed images. That's the message of what Cypher was talking about in The Matrix and what happens at the end of the movie, that if you get the actual code of the Matrix, you're able to do more with that information than you are able to do with the processed video image that's processed for the human mind to see. Since the computer is more sophisticated than the human mind, it's able to do more with that data than we would be able to do. So Elon's going to explain here how this leads to ultimately autopilot FSD will become better than human.
The cars will maneuver with superhuman ability and reaction time much faster than a human. I mean, I think over time, the autopilot full self-driving will be capable of maneuvers that, you know, are far more than what like James Bond could do in like the best movie type of thing.
That's exactly what I was imagining in my mind as you said it.
Like impossible maneuvers that a human couldn't do.
So if you think about that, Neo at the end of the movie is able to do superhuman things that other human type characters aren't able to do, more than even the agents, the Matrix's agents are able to do. He becomes super powerful. And the idea, again, I think it's a little bit of a stretch, but I think the idea here is by using the raw photon counts, by using computers that don't get tired, don't get sleepy, and are able to have incredibly fast reaction times, you're able to actually drive a car better than a human would be able to drive it. I don't know about the James Bond sequence stuff. I think that may be pushing it, but just being phenomenally good at driving a car by comparison. I wonder if we're going to see FSD drive the Nürburgring or some racetrack and see whether it'll be able to outperform a human driver at some point. That would be something I would be impressed to see, and I think it will ultimately do it.
Well, let me ask, sort of looking back at the 6 years, looking out into the future, based on your current understanding, how hard do you think this full self-driving problem, when do you think Tesla will solve level 4 FSD?
I mean, it's looking quite likely that it will be next year.
Just a couple of things to be clear about. First of all, I personally don't like the term level 4 and level 5. And you'll notice Elon didn't use that term. But Elon's talking about better than human, and it'll be next year. And when he says next year, this interview happened in 2021, I think November or December of 2021. So he's talking about by the end of 2022, which is the year we're in now. He just tweeted the other day that FSD beta version 11 is lit or hot or fire or whatever. So we're going to see more about that soon, I think.
And what does the solution look like? Is it the current pool of FSD beta candidates, they start getting greater and greater as they have been degrees of autonomy, and then there's a certain level beyond which they can do their own, they can read a book?
They can read a book, meaning the driver no longer has to watch and can read a book while the car is driving itself. That's what Lex meant there.
I mean, you can see that anybody who's been following the full self-driving beta closely will see that the rate of disengagements has been dropping rapidly. So like a disengagement be where the driver intervenes to prevent the car from doing something dangerous potentially. So
I just want to know here, because I drive FSD beta, I intervene more than I have to. I intervene because I want to get somewhere quicker than FSD beta will drive. FSD beta is a very cautious driver. And if I see a light up ahead that I think I can make by driving fast and making a couple of quick lane changes, then I'm going to gun it to make the light, which FSD beta won't do. And I would say if I'm doing a 20-minute drive with FSD beta, I can probably do it in 16 minutes myself. So if you're in a hurry, FSD beta is kind of annoying because it's not as aggressive a driver as I am. If you're not an aggressive driver, then FSD beta is fantastic. And so there's two kinds of disengagements. There's disengagements because I'm in a hurry and I don't want to wait for FSD beta. There's disengagements because I want to take a different route than FSD wants to take. And there's disengagements to avoid a crash, right? That's the really important disengagement, is when FSD beta is going to do something bad that's either going to create a dangerous situation or actually cause a crash. That is when an intervention is important. An intervention to get there quicker is not as important because the goal is to get full self-driving working better than human, not faster than human. Safer than human, not faster than human.
The interventions, per million miles has been dropping dramatically. At some point, and that trend looks like it happens next year, is that the probability of an accident on FSD is less than that of the average human, and then significantly less than that of the average human.
When he's talking about disengagements, he's talking about dangerous disengagements. Not Warren's trying to make a light disengagements, but actual dangerous situations. They have internal data at Tesla where they're measuring how FSD beta is doing, and they're able to see things we're not able to see. My individual experience with FSD beta is not the same quality of data and quantity of data that they have inside Tesla's home office on the autopilot team and the AI team. They're able to see and measure a lot about what's going on with FSD beta, and they can see the improvements that we can't really see. And so this level of measuring disengagements, they are monitoring everything, they are tracking everything, and they are seeing that this number of dangerous disengagements is falling so fast that by the end of 2022, it should be safer and significantly safer than the average human driver.
It certainly appears like we will get there next year. Then of course, then there's going to be a case of, okay, well, we now have to prove this to regulators and prove it to, and we want a standard that is not just equivalent to a human, but much better than the average human. I think it's got to be at least 2 or 3 times higher safety than a human. So 2 or 3 times lower probability of injury than a human. Before we would actually say, like, okay, it's okay to go. It's not going to be equivalent. It's got to be much better.
I don't necessarily agree with that goal, but I understand it from a public acceptance point. If you're going to be putting this in public, you want it to be significantly better than the average human. My view is if it's better than the worst human, and the first humans who stop driving are the worst humans, the first humans who use robo-taxis instead of driving themselves are the worst humans. If you're taking the worst drivers caused most of the accidents. The bottom 10% of drivers cause 90% of the accidents. Maybe it's the bottom 20% cause 80% of the accidents. I'm not sure which, but as long as FSD beta is, let's say, 25th percentile, it's better than a quarter of the drivers. If the end result of having robo-taxis is the worst drivers who have the highest insurance rates and the highest cost per mile of driving, if we take those people off the road first and get them in robo-taxis, we've made the road safer, even if it's not better than the average human. But from a public policy, from a media perspective, from all the negative pressure you're getting from governmental agencies and special interests, getting it significantly better than the average human is probably a much better choice. Unfortunately, politics gets in the way, media gets in the way of actually making the world safer for humans. And the time between 25th percentile and 90th percentile isn't that big of a gap anyway, so it's not going to matter that much. But ultimately, this is going to cost a few human lives, making it wait until it's that much better. Next, Elon's going to talk about version 11, which, remember, this is a few months ago now. I think version 11 is coming soon. I'm on 10.10.2. Elon just tweeted about version 11, so I'm hopeful we're going to see it soon. Listen to what Elon says about version 11.
The FSD 10.6 just came out recently. 10.7 is on the way. Maybe 11 is on the way somewhere in the future.
Yeah. We were hoping to get 11 out this year, but it's 11 actually has a whole bunch of fundamental rewrites on the neural net architecture and some fundamental improvements in creating vector space.
There is some fundamental like leap that really deserves the 11. I mean, that's a pretty cool number.
Yeah. 11 would be a single stack for all, one stack to rule them all.
One stack to rule them all. The way FSD was working before was there was a stack, a set of programming for how to operate in a parking lot, a stack for how to operate on an interstate highway, and a stack for operating on city streets. So there would be this changeover. You're coming out of a parking lot onto a city street. It would change over from the parking lot stack to the city street stack. You're getting off a highway and going onto city streets, there's a handoff there. And my personal experience, which is probably wrong, but my general sense is that moment of transition from one stack to another sometimes created problems. I'm not sure that that's true, but the hope is that once you get down to one stack, number one, that one stack improves more because it's getting more data, and that one you avoid the handoff problem of going from one stack to the other.
But there are just some really fundamental neural net architecture changes that will allow for much more capability, but at first they're going to have issues. So like we have this working on like sort of alpha software, and it's good, but it's basically taking a whole bunch of C code and deleting a massive amount of C code and replacing it with a neural net. And Andre makes this point a lot, which is like neural nets are kind of eating software. Over time there's like less and less conventional software, more and more neural net, which is still software, but it's still comes out to lines of software. But it's more neural net stuff and less heuristics, basically.
Neural net means the vehicle, the hardware learns how to drive. Heuristics is a human codes it and says, if this happens, do that. Heuristics is humans like describing when you confront this situation, this is how we want you to handle it. And if you can get away from heuristics and you can have the machine learn to drive using machine learning, in the long run, that's largely going to be better in a variety of ways. So more and more of the code that allows the car to operate is becoming machine learning based instead of human coded heuristic programming.
Like right now, the neural nets deliver a giant bag of points to the C++ or C and C++ code.
Yeah.
We call it the giant bag of points.
Yeah.
And it's like, so you got a pixel and something associated with that pixel. Like this pixel is probably car. This pixel is probably lane line. Then you've got to assemble this giant bag of points in the C code and turn it into vectors. It does a pretty good job of it, but we need another layer of neural nets on top of that to take the giant bag of points and distill that down to vector space in the neural net part of the software as opposed to the heuristics part of the software. This is a big improvement.
Neural nets all the way down is what you want.
It's not even all neural nets, but this will be just this is a game changer to not have the bag of points, the giant bag of points that has to be assembled with many lines of C++, and have a neural net just assemble those into a vector. So that the neural net is outputting much less data. It's outputting this is a lane line, this is a curb, this is drivable space, this is a car, this is a pedestrian or a cyclist or something like that. It's outputting. It's really outputting proper vectors to the C control code as opposed to the sort of constructing the vectors in C.
In the past, the neural nets generated some information that then human-generated code had to convert into a vector space. And we're skipping ahead to where the neural nets take in the photons and they convert that directly to a vector space. And that should make things quicker, and it should make the computer work more efficiently than it was worked before. Not perfect. They got some challenges. They were in alpha in December of 2021. We're already in late February, and we're still not seeing version 11 in beta cars. So it's a lot of work to get it working, but it's a potentially fundamentally big improvement.
Which we've done, I think, quite a good job of, but we're kind of hitting a local maximum on how well the C can do this. And just all of the networks in the car need to move to surround video. There's still some legacy networks that are not surround video. And all of the training needs to move to surround video. And the efficiency of the training needs to get better, and it is. And then we need to move everything to raw photon counts as opposed to processed images.
Okay. So
which is quite a big reset on the training, because the system's trained on post-processed images. So we need to redo all the training to train against the raw photon counts instead of the post-processed image.
So ultimately, it's kind of reducing the complexity of the whole thing. So reducing
lines of code will actually go lower.
Yeah, that's fascinating. So you're doing fusion of all the sensors, so reducing the complexity of having to deal with each
Fusion
sensor.
of the cameras is there's not cameras really.
One interesting detail here is it's not just about cameras. Lex asked him this great question about audio, that will the cars need to use audio? So listen to this.
You're doing fusion of all the sensors, so reducing the complexity of having to deal with each
Fusion
sensor.
of the cameras is there's not cameras really.
Right. Yes.
Yeah.
Well, I guess we got ears too. Okay.
Yeah. We'll actually need to incorporate sound as well, because you need to listen for ambulance sirens, right, or fire trucks yelling at you or something. I don't know. Just there's a little bit of audio that needs to be incorporated as well.
So that's an interesting detail, and it seems like that could be a big challenge. Does it need to interpret words and figure out what they mean and follow directions from people? That's something that probably will have to be developed along the way. I'm not sure how critical it is in the early days. And I think, one theory about robotaxis is that you can have remote operators who are available in rare cases where the vehicle needs help, that a remote operator could interpret what's needed. I don't think he's talked about that, but I think that's something that might be necessary at some point. So the last bit here, check this out, the really last chunk of what's in what Elon talked about with Lex about FSD.
The idea of going to the moon is the easy part, but going to the moon is the hard part.
It's the hard part.
And there's a lot of hardcore engineering that's got to get done at the hardware and software level. Like I said, optimizing the C compiler and cutting out latency everywhere. If we don't do this, the system will not work properly. The work of the engineers doing this, they are like the unsung heroes to some, but they are critical to the success of the situation. Yeah,
just the whole infrastructure, the software. I mean, everything is going on with data engine, whatever it's called. The whole process is just a work of art to me.
The sheer scale of it is boggles the mind. Like the training, the amount of work done with, we've written all this custom software for training and labeling, and to do auto labeling. Auto labeling is essential, because especially when you've got surround video, it's very difficult to label surround video from scratch is extremely difficult. It take a human such a long time to even label one video clip, several hours. Or the auto labeler, basically we just apply heavy duty, a lot of compute to the video clips to pre-assign and guess what all the things are that are going on in the surround video.
And then there's correcting it.
Yeah, and then all the human has to do is tweet, say this, adjust what is incorrect. This is increases productivity by 100 or more.
That's one more piece of the puzzle. Is auto labeling is a big part of what enables the Tesla autopilot team and AI team to be much more efficient in learning and training the system. The system is able to look at a scene and identify what objects are, and then rather than the individual human having to identify every object in the scene, the human only has to identify what's incorrect and correct it. And that saves a ridiculous amount of work, and it makes it much easier for them to get where they need to go. So the thing is that if the car is reacting to information that came in and it has to wait an extra 13 milliseconds to react, that makes the car's reaction 13 milliseconds later than it should be. So if you can save 13 milliseconds by skipping the image processing step, and the car can process the raw photon counts instead and use that to drive the car, then you've just made the reaction that much closer to when it needs to be. And at the same time, there's more information in the raw photon counts than there is in the processed imagery. So there's a bunch of advantages to what they're doing, and this is coming in version 11. It's amazing to me, by the way, that the CEO of a company, there's no way that Mary Barra of GM or the CEO of Ford Motor Company or the CEO of Volkswagen is this deep into the self-driving program in their company, that they understand what C compiler they're using and what their latency and jitter issues are. And any of these companies, it's so striking how deep Elon goes on whether it's rockets and what kind of motor engine they're using, and whether the chamber is melting at a certain temperature. The level of his depth is just striking and really impressive. So I just wanted to show you something else to give you a sense of this idea of modeling the world in 3D. You can see here that we've got a car driving through space, and the car is identifying objects as it drives through. And you can see, for example, that it's identifying light towers, it's identifying cars, it's identifying lane lines, it's identifying, all sorts of things. It's identifying how far away they are, how fast they're moving, maybe more properties of the vehicle. And these are all vectors that are being assessed by the system as it is driving. And this is effectively building a vector space model or a 3D model of the world. It's trying to understand the world around it. As the better it understands the world around it, the better it's able to navigate the world around it. That's the big challenge. And this is a fairly old video. I'm not sure exactly who's captured this. I think this maybe came from Green the Only. You can see the challenge of identifying all these objects, understanding what they are in terms of identifying it's a sedan, it's a pickup truck, it's a tractor trailer. We're in a right turn lane here, so it's got to figure out how to make this turn. And you can see the tether is adjusting to see where are we going. There's all these different things that are going on with this car that it's got to figure out. So the first challenge is to develop this 3D model of the world, vector space model of the world. And then once you have a really accurate, trustworthy, reliable model of the world, it becomes much easier to plan how you're going to navigate in that world. That's the goal. That's what I think is, as we're waiting for FSD 11 and future development on FSD, the number one task is to make better predictions of the world, better identifications of objects, better predictions of what objects are going to do with shorter latency and shorter jitter. And the better that they're able to achieve those goals, the better the easier it becomes to navigate that world. That's the big challenge. So people get caught up in other things like, how does it handle this roundabout, or how does it handle this problem? And we all have our own individual experiences with FSD beta. But the larger issue, the one that's harder for us to comprehend, is what they're doing to try to get a better picture of the world. And I think we'll see. I think when version 11 comes, we're going to see the vehicle perform much better because it does a much better job of recognizing the world around it. And particularly with the use of raw photon counts, we're going to see better understanding of the world around, because raw photon counts have more information than digitally processed images. And reduced latency, reduced jitter allows the vehicle to make decisions more quickly and more appropriately for the world around it as well. And you have a better sense of the world around you because you've eliminated the latency, and you've reduced the latency and you've reduced the jitter. These are all things that need to get done. I'm expecting that we're going to see a lot of that. I think people are focused on the one stack to rule them all. I don't think that's the biggest advantage of version 11. The biggest advantage of version 11 is getting to this point where using raw photon counts makes the visual information coming in richer and enables a better depiction of the world. The latency and the jitter, all of these things are going to make a much better process. And there's so many other things going on, whether it's a better C compiler, so many different things that are happening, auto labeling. Dojo is going to come online at some point, and that's going to improve training. I've actually heard from someone related to NVIDIA that NVIDIA is actually making a lot of progress on their AI training, and it may mean that Dojo ends up being irrelevant. We'll see. I think Dojo is ultimately going to outperform NVIDIA, but we'll see. The NVIDIA supercomputers are doing a great job for Tesla already. I hope you're excited about version 11 of FSD beta coming soon and getting closer and closer to a system where FSD is better than the average human. And you can see with those improvements that I described, As it gets a better picture of the world, it gets a lot easier to navigate, and it becomes a lot more likely that you're going to achieve better than human driving. That's what we're looking for. I'm excited about it. If you like this video, please check out my other videos. Please check out the t-shirts on elonbits.com, the stainless steel water bottles as well on elonbits.com. Check out my channel, The Daily Lie, on Locals, warrenredlich.locals.com. And thank you so much for watching.